This is the cooling loop design for the MSU Computer Center using the shell and tube heat exchanger. I am Drew Goodman.
And I'm Alex Figa.
The main goal of this design is to design a shell and tube heat exchanger to cool down the computer system at Michigan State University, the engineering building. And the reason for this design is because of the high cost of the standard refrigeration unit. And the shell and tube heat exchanger design uses a more environmentally safe reservoir holding the drinking water to cool down the computer center.
So, kind of like how Drew said, basically we're using, instead of the costly cooling system that's already in place for the computer center, we're going to be using drinking water from a reservoir that's roughly 600 or so feet away from the engineering building. That's going to get pumped in to the heat exchanger in the engineering building. And then, so the cooling fluid for the computer center will be cooled using the drinking water. Um, the computers roughly generate 0.6 megawatts of thermal energy, and the reservoir flows roughly 1 million gallons a day of the drinking water. Kind of one of our limitations was we couldn't have the drinking water rise in temperature more than 3 degrees. And kind of the dimensional constraints we had was the heat exchanger had to be less than 25 feet, and the current piping is a 12-inch inner diameter. We were specified to use a shell and tube design, a shell and tube heat exchanger design, and obviously we're using the Aspen One software.
Um, this was the our cold stream and our hot stream compositions for the heat exchanger. So the cold stream composition was the drinking water, and this was just regular drinking water that went in, and that's the cold stream. And then the hot stream was the water and the propane diol. And this was a 50-50 split between the drinking water and the propane diol. Um, and that was after it. That's the hot stream, and that was after it cooled down the computers.
So kind of like Drew said, we used 100% distilled water as our composition in the cold stream, as that's going to be the drinking water. So we didn't want to add anything. We didn't want to add any kind of uh, any other kind of fluid to that. Um, so, and then for the hot stream, we used a 50-50 mixture of the distilled water and the propylene glycol. And we used this because that hot stream fluid is strictly being used to cool the high performance computing center, and we didn't have to worry about it being used as drinking water. And we thought the lower freezing point that we get from the propylene glycol and distilled water mixture would be beneficial, since the heat exchanger would most likely, it could be positioned outside the building, and if the system was ever to shut down in the winter, it wouldn't freeze.
This is the what we input into the Aspen One um, technology designer to create the proper design for our shell and tube heat exchanger. And the mass flow rate for the hot stream was 10 kilograms per second, and the mass flow rate for the cold stream was 43 kilograms per second. We decided on the 43 kilograms per second because that was like the unit conversion from 1 million gallons a day of water. And then the 10 kilograms per second was decided because that just fit with the 43 kilograms per second well. And then the temperature for the hot stream, this was just the maximum temperature, so we decided to put the maximum temperature that we were allowed, which was 120 degrees Fahrenheit. And then for the cold stream, the 56 to the 59 was the 56 was the original temperature, and it was allowed to go up to 59 degrees. So yeah.
Yeah, so kind of elaborating more on what Drew said. Uh, the hot stream we had the water propylene glycol mixture, and we chose the inlet temperature of 120 degrees, which is kind of outlined in our design parameters for this project. We chose a pressure that was slightly lower than the cold stream we calculated in order to keep the mixture as the hot stream. As if we had it as a higher pressure, it would flip to the cold stream, and so that kind of limited us, and we had to choose a lower pressure for that. We chose the mass flow rate as it wasn't really necessary. The 10 kilograms, it wasn't necessary to really go any higher than that, which would kind of minimize the size and cost for the pump for that fluid. For the cold stream, we had our limitation between 56 and 59 degrees Fahrenheit, which was also outlined in our design parameters. And we chose to utilize the full 3-degree increase in temperature to maximize the amount of heat transfer between the fluids. Yeah.
So this is our just how we designed our heat exchanger, and the TEMA type was CEL, and this was just our tube outer diameter. We decided on like the default of 0.75 inches, and the 30 triangular, that's just how the tubes are laid out. And the material we used was stainless steel 304. And over here, I don't know if my mouse is able to circle it. This was the inner diameter that we selected, just because we had to get it near 12 inches.
So we decided to use a 304 stainless steel construction for the heat exchanger design. We chose this because it's a food grade material that's also corrosion resistant. This choice of material did bring the cost up a little bit, but it should last a lot longer and need less frequent service. The TEMA configuration we landed on consists of the C being the integral tube sheet and removable bundle, E being a one-pass shell, and the L being the removable channel with a flat cover. We chose the C and L because we thought it would make it easier to clean with the removable pieces. So we knew having a cleanly system is important because we were going to be using the drinking water through it. So frequent cleaning would be ideal. And we also chose the one-pass shell because it was a lot cheaper than all the other options, and it still retained the same amount of heat exchanged.
This is just our TEMA sheet on the finished product of the shell and tube heat exchanger. And we were only able to exchange 0.325 megawatts of thermal energy, not the full 0.6 megawatts of thermal energy. And this just gives the whole just breakdown of what our heat exchanger does.
So this is kind of just more of a visual kind of overlook of the heat exchanger. On the left hand side is kind of like the whole heat exchanger, and it kind of shows the inlets, the outlets, the length of the whole thing, which is roughly 106 inches. And then on the right shows like the cross section view with all the little tubes. So that would be what the drinking water is passing through, and the shell is like the bigger outer circle, which the hot stream and like the computer cooling fluid would be flowing through around those tubes. Oh, the roughly the outer diameter is roughly 12 inches.
So after we designed all this and went through the different combinations we could make, we decided that this design would be the best for this assignment, and the overall length of the heat exchanger is 106.375 inches, which is about 9 feet, which is much shorter than the maximum. And the outer diameter is roughly 12.3 inches, and it exchanges 0.325 megawatts of thermal energy. A larger design did not improve the amount of heat exchanged in the system, so we decided to keep it smaller, which allows for a wider range of placement options for the heat exchanger, and it helps save money, which helped rationalize the use of stainless steel construction.
So for the pump sizing, from the design parameters, we knew that in order to pump the drinking water from the reservoir and to the engineering building, we had the following constraints. We had a volumetric flow rate of roughly 1 million gallons per day, a 12-inch inner diameter pipeline that runs a total of 623 feet, a pump head of 10 meters to get up to the third floor in the engineering building, and at least one inlet from the reservoir to the pipeline, one ball valve in case you wanted to turn the flow off from the reservoir, and then the pipeline overlay shows two 90-degree elbows, and then we would also need another 90-degree to go up to the third floor, and then over another 90-degree to go over into the heat exchanger. We found that to meet this required volumetric flow rate and with the pipe length and minor losses, we would need a pump outlet pressure of around 19.2 psi. And then we found that a total of about half a psi would be lost between the pump outlet and the heat exchanger inlet. So that's kind of why we used the pressure of 18.73 psi at the inlet of the cold stream. Using the typical pump performance curve for a Taco Model 4013 pump, a pump with 10 horsepower and 60% efficiency is required to sustain a volumetric flow rate of around 644 gallons per minute and a pump head of 10 meters.
So after doing some research, a suitable pump for our application would be the Bell and Grosset E1510 series 3BD pump. According to the pump curve, um, we would need the 10 horsepower model to accommodate the flow rate and total head we have, which is marked by this green dot right here. And this pump can be purchased at the nationalpumpsupply.com for $9,847.
So for the heat exchanger, it looks like able to we were able to source like exactly kind of the dimensions that we needed and the size and the material and construction from the Custifab website. This company kind of designs heat exchangers that can be specified for shell and tube designs and meet the correct specification for our usage. Custifab is like a top designer of heat exchangers and should suit our design specifications perfectly. We would probably we were unable to get a like an exact dollar amount for the heat exchanger because we had to send in like a quote, but if we needed to, we could send in a quote and get an estimate for how much it would cost.
So overall, our objective was completed by removing some of the 0.6 megawatts of thermal energy. Um, Using the reservoir overall can be deemed as a cost-effective and environmentally responsible way for cooling the computers in the HPC. And ways this can be improved would be an increase in the flow of drinking water from the reservoir, or if the temperature of the drinking water could be raised a little more. Overall, though, more than half of the heat produced by the HPC can be dissipated through the drinking water that has already been flowing to the building. And we believe this to be a worthwhile project due to the energy, money, and environmental waste savings. So that's our report on cooling loop design for Michigan State's HPC Center.